I'm sorry, everyone. Did everyone try this? Hope you have not forgotten. How many of you got the answer? And how many of you forgot? Sent on WhatsApp. I think I saw it. Equations looked right. You got the same answer, Aryan. Let's see. Let's see how to do this thing. Last month, if you see, there were 2 additional tests. Most of you didn't even bother to give, I guess. Some of you are requesting to extend it, so I'll be extending it again. So do make sure to give. I know your major test is coming up, so it'll be good practice papers for PACE people at least.
They're keeping it till the month end.
हाँ क्या फायदा मंथ एंड वो लास्ट टाइम तो मंथ एंड ही रखा था पूरा व्हाट डिड यू गाइस डू you guys didn't even remember also you have abandoned it like a child on the road you guys are like you guys are like cruel parents who abandon their children
Listen, now major test is
Now
coming
major
soon.
test has come now.
देखा only when major test comes we'll take care मतलब only when the kid becomes rich and successful then we will go and say ये मेरा बच्चा है नहीं तो abandon कर लेंगे उसको we can see the evil traits चला I was just scared for a moment like I thought पूरा app crash हो गया मेरा पूरा note चला गया I was scared. Restart किया तो set हो गया. चलो. How to do this thing? First thing, you have pulled it apart by A. So for the hollow sphere and the solid guy, let this go by x1. Let this go by x2. Let this acceleration be a2. Let this be alpha 2. This friction is f2 and this guy will be kx, where x is the elongation and the spring. So this is kx. This is f1. This is a1. The headache is this, everything is different here. Here we have x is equal to x1 plus x2, where x is the elongation in the spring. So when you pulled both the things by x apart, let's assume this thing has mode x1, that thing has mode x2. There's no guarantee both will move equally. Since there is no slipping, I can take my torque at the lowest points always. Now see, I'll tell you the problem here, you know what? You should get A1 in terms of what? A1 should be in the form of minus omega square x1, na? Are you getting the catch? You should not get A1 in terms of x and say this is omega square. This is a blunder. If you're displacing by x1, the acceleration is a1. So a1 should be proportional to x1. So here, if you take torque about A, then this guy would be minus kx into r is equal to, this is hollow sphere. Solid sphere. This will be 2 by 3, so 5 by 3 mr square. Two by 3 mr square plus mr square, parallax theorem, alpha 1. Similarly, torque about B will be kx r is equal to 7 by 5 mr square alpha 2. So from here we can write r alpha 1, that would be a1, which is r alpha 1 will be minus 3 kx by 5m. And here this guy would be a2, which is r alpha 2, which is 5kx by 7m. Now what we are interested is, we want a is equal to a1 is equal to minus omega square x1, or we want a2 is equal to minus omega square x2. A is not equal to this thing. So 1 and 2. If you divide a1 by a2, you will see something interesting. Minus 3kx by 5m, 5kx by 7m. They're always in the ratio of 21:25. So therefore, we can also conclude that displacement x1 by x2 also should be in the ratio of 21/25. Does it make sense? If the acceleration is in that ratio, then displacement is also in the same ratio because a is proportional to x1 and a is proportional to x2. Got till here? अभी क्या करना है? Finish it off. I'll give you a minute. I did everything. सिर्फ थोड़ा solving बाकी है. Now you guys try. What scares in this problem is a1, alpha 1, a2, alpha 2, f1, f2. Everything is different for both of them. That's what makes problem look scary, but इतना है नहीं. Finish it off. You got a minute. Now Aryan did the same na so far. Yeah. हो गया क्वेश्चन. This will be a good question advanced level में. So a1 is minus 3kx by 5m. And I know x1 plus x2 is x. x1 by x2 is 21 by 25. So from here, this is x1, x2 will be 25, x1 by 21 is x. So x is equal to 46 x1 by 21. So ये पे डाल देते हैं. a1 is equal to minus 3k by 5m and this guy is 46 by 21 into x1. There, that's your omega square का term. That is 46k by 35m. Most common mistake what people do now, they think a is equal to minus omega, a1 is equal to minus omega square x. This is your omega square. Time period is root over 2 by 35m by 36k. Did I give the same or reverse? And amplitude क्या होगा? Same thing, no? x1, a1 by a2 should also be in the ratio of 21:25. Therefore, a1 will be 21 by 46 of amplitude. a2 will be 25 by 46 of amplitude. Clear? Any doubts on this? Thermodynamics वाला problem किया ना? किया. Let's see one more. You have a solid hemisphere. Mass m, radius r. There's no slipping, it's a rough floor. It is slightly disturbed. So what will happen? It will rock now. Did you ever sit on that rocking chair? It will oscillate like this. So find time period for small oscillations. Just get me the equations. For the major test, right, the best thing to do is write the practice test and go through the notes. You still have 3 weeks of time. Start doing it from now. There is no other better way of revising. And if you see now, the practice test also, I mixed a very weird topics: rotation, ray optics, heat and thermo, ray optics. So it will be a good mix. And a mechanics paper we are in next week. And there's one mechanics paper also for practice. So you have ample of papers, like 4 or 5 papers. Think of like this now. If you solve the paper like an exam, and if you take another 1 hour to resolve, it takes 2 hours. You can finish your major risk preparation with something like 8 to 10 hours in the next 3 weeks. Physics, that is the only way to do. There is, unlike chemistry or maths where you sit and solve hundreds of problems. Physics you can revise with like what 50, 60 problems. Say you can revise more than half of the concepts. How do we do this? Your seniors ka tests are starting from tomorrow. GE means round 2. How do you always start? Disturb it by a small displacement. I'll help you with the free body diagram. I'll exaggerate the figure a bit. So initially this was that center. Let's call it O. The center of mass was somewhere here. So, so when you displaced it, ये theta था. So you need to find alpha in terms of theta. This is alpha. This is normal reaction. This is friction. This is mg. Isn't it? This is how the FBD looks. If you displace by small theta, there are 3 forces. And you know which point you have to take the torque and finish it off. V is R omega. Why the hell you need V is equal to R omega? It is just rocking, right? Like a chair. Did everyone get the free body diagram? If you displace by theta, see the restoring forces, find torque is equal to I alpha, and then you get alpha proportional to theta. And then whatever is left out is SHM, omega square. Try. You got a minute or two. See, we will take this point as A. So torque about A, N ka torque is 0. This torque is 0. Only mg will be there. I'll draw one more diagram. This is point A. This is mg vector. So perpendicular distance from the axis would be this guy. Where is the center of mass for a solid hemisphere?
3r/8.
3r/8. Yep. So ये perpendicular distance जो है, that guy will be 3r/8 sine theta. That's your r perpendicular. So torque about A will be mg 3r/8 sine theta is equal to minus I about A alpha. I about A कितना होगा अभी? So IO will be 2/5 mr square, which is nothing but ICOM plus m into parallaxis theorem 3r/8 whole square. IA will be ICOM plus. Shit, these distances are bad. ये distance निकालना पड़ेगा. Which is actually, I exaggerated the figure too much. If you see now, the distance is actually almost theta is negligible. It should be 5r/8. If you actually look at the figure now,
Sir, then theta negligible है, so that torque के वहाँ पे भी you'll change sin theta to theta.
थीटा, हाँ नहीं तो अभी SHM कहाँ से आएगा गॉड?
हाँ हाँ.
ये A था, तो दिस इज ऑलमोस्ट द सेंटर ऑफ मास ना. ये 3r/8 था, ये 5r/8 था. That is a catch of small oscillations. So are you getting ना? I exaggerated the figure too much. चलो फिर भी कैलकुलेट करना ही है ना. We can do that also. We can drop a perpendicular here. This will be 3r/8 sin theta minus this thing, square and all that stuff, but you'll get the same thing. So you can write center of mass now. Let's call it as C. So CA is approximately 5r/8 since theta is small. So you solve from here, तो IA आ जाएगा. And for small angles, we know alpha, this guy will be 3mgr/8 IA theta. That's your omega square. Clear?
So in objective type, they will do this, but in numerical, are they expecting us to find the value of that distance?
What are you talking?
Whether like in numerical, will we have to find the exact distance for that this thing for the moment of inertia?
Not required. You're taking small theta ना रे. तो calculate करके देखो end में तुझे भाई आएगा.
Okay.
You will get something like 5r/8 into 1 minus cos theta times something ऐसा कुछ आएगा term, 1 minus sin theta times. Like I'm saying ना, the figure I exaggerated so much ना, it gives you a feeling it is weird. But चलो, I'll calculate. इतना भी करने का जरूरत नहीं है. This triangle is there, OCA. Triangle OCA. Use sine rule ना. CA by sine theta is equal to, do I know any other angle? I don't know. Actually, I know the distances ना. Cos theta will be OC square plus OA square minus CA square by 2 OC OA. Cosine rule use कर. You know OC? 3r/8. You know OA? R. सब आ जाएगा. And cos theta is very small. This will tend to 1. Clear? ऐसा भी कर सकते हैं. Cos theta will tend to 1, and from here you will get CA का value. If you do that, you'll get the same thing. Any doubts on this? All got this? Let's see one more. Ali, Udayan, clear with this? Molika? Clear, na? Vartika, Rehan? We have a hemispherical bowl. Radius R. No slipping. Basically, it is rough. Inside, you kept a solid sphere. M and small r, solid sphere. There, it is disturbed by small angle theta. So what will happen? This ball will roll like this and go, na? You getting? See, if it is smooth, na, it will go like this, like a pendulum. But here it is not slipping. The ball will roll and go. Able to visualize? And will roll and come back. Find time period for small oscillations. You're getting a feeling of rotation, na? Feeling nahi hai, rotation nahi hai. Get it? And SHM comes and hijacks the problem. Try. Give it a try. Just give me a minute. Answers? Omega root 5g 7r minus r. Okay, looks right. Here, na, you have to be careful about one thing. The alpha you're talking about is something else. See. So when you displace this, what you're interested is this alpha. Okay? But this pair here is going with A, and let's call this thing alpha dash. You're getting? The sphere will have its own alpha dash, and the whole thing is rotating with alpha. What we are interested is alpha is equal to minus omega square theta. You want the relation between alpha and theta. But what is alpha here? Alpha is nothing but acceleration of the center of mass by r minus small r. Isn't it? From the center to this angle, you want this rotation, isn't it? So that will be this acceleration by this distance will give you alpha. Is that making sense?
सर हमें टाइम पीरियड किसका निकालना था बाउल का
बाउल तो रेस्ट में रहेगा फिक्स्ड हेमिस्फेरिकल
सर वो
ट्रैक है वो
हाँ ओके दैट सो दैट वो डिफरेंट अल्फा किसका है
ये बॉल का
वो बॉल तो यू टुक एज अल्फा डैश एंड दैट अदर
अल्फा डैश है this alpha is rotation of this change of acceleration of this angle na there are two different rotations here यहाँ पे it is like एक rotation है, एक revolution है. Understood? Alpha is for the revolution. Alpha dash is for the rotation. All got the steps here? You're finding when you say alpha is equal to minus omega square theta, which alpha you're supposed to take? It is not alpha of the rotation, it is alpha of the revolution. Because देखो ना, when you change this theta, you want this alpha ना, why do you care about this ball का alpha dash? Is that making sense? And alpha is nothing but acceleration of the center of mass of the sphere by the distance between them. So now what to do there? Then let's draw the FBD there. Friction mg sine theta a dash alpha dash. Take this point here A. The torque about A will be mg sine theta into small r is equal to minus IA. It's a solid sphere. 7/5 mr square alpha dash. So A dash will be small r alpha dash, which is minus 5g by 7 sine theta. Take this and put it here. Pi g by 7 theta by r minus small r. This is your alpha dash. For small angles, we can write alpha dash is equal to minus 5g by 7 r minus r theta. The time period is 2 pi root over 7 times r minus small r by 5g. Check.
So otherwise, you can just directly use the result, right? That g sine theta by 1 plus k square by r square.
हाँ वो भी कर सकते थे. But that's for an incline, na? Meaning if you understand that, it works.
But like small theta, no?
Yeah, it works. Clear? Next one. Can we conserve energy to get omega? Yeah, you can. We have energy method. I'll teach you. But I am really not pro with it. I don't like it much. But it is useful in some special cases. So we will do. Clear with this? Next one. Just to give an idea here, rigidly connected to P. So there is a hinge here. There is a hinge here. This is connected to the rod here, and there is a spring also here. This is connected here. This no diagram. It is connected here. So we have a rod here. This is a rod. Let me see if I can draw a new diagram. This is one string K1. This is one string K2. There is a hinge. This is the center. This is also hinge right over here. You're getting it? So if I disturb this, just to give an idea, how will the shape become? The disk will rotate a bit. This rod will become like this. Isn't it? If you twist the disk a bit, the whole rod will rotate like this, meaning not exactly like this. ऐसा कुछ rotate होगा. So if you rotate the disk like this is how the rotation would be. And the whole thing will start rotating. This is R, this is also R. This is R and this is 3R. I think it's a good one. Again, theta is quite small. Let me help you with the diagrams here. This is P, this is Q. Now, if you displace this disk by small theta, this is what will happen to the rod. This rod also rotated by small theta, na? Isn't it? Now there are two things happening here. See, this is the thing. Now, because the rod rotated, this guy will go up by r theta because that length was r. This guy would this got compressed by 3r theta because this length was r and this length was 3r. Agreed? Because the rod rotates. On top of it, because the disk is rotating with theta, from the top, this will go down by another r theta. You're getting it? And this point here will again go up by another r theta. There are two things happening. Because the disk is rotating, spring is compressing. Because the rod is twisting, the spring is compressing. So the net force, if you look on the disk, so this r theta is the compression due to rotation of the spring, a rotation of disk. So the springs are getting affected due to two things, the disk and the rods. This is a compression due to the rod. Again, theta are quite small. That means if you draw the FBD of this spring force will be K1 into compression is 2r theta. This guy is also compressed, so it will push. Sorry. K2 into 4r theta. On top of it, there is also the tension in the rod. And because of this whole setup will rotate with alpha. So if you take torque about the center,
the tension of the rod will be directed downwards.
no, it will be, there will be two components actually. We are taking only the vertical component. Tx ty होगा ना? You want, I can call this as ty. So K2, 4r theta into r plus K1, 2r theta into r plus tension due to y into r should be equal to minus I center alpha. अभी ty निकालना है. How to find the tension? If you look at the FBD of the rod, remember the rod has become like this. So this was the tension, which is basically tangential here. Like I said, I'm exaggerating the figure. It's actually almost vertical only. And this will be the spring force, which is K2 into 4r theta. This is P, this is Q, and this is the axis of rotation. So torque about PQ axis will be T into this distance is R and this is 3R. Is equal to I alpha, but here I is 0 since rod is massless. This is one advantage of massless rods. So we get tension is 12 K2 4 theta. Have a look at this. Then once you got the tension here, take it and dump it here. So this tension T is 12 K2 R theta. Substitute here, how much is this? 4 K2 R square theta plus 2 K1 R square theta plus 12 K2 R square theta minus M R square by 2 alpha. So alpha will be minus 32 K2 plus 4 K1 by MR theta. I goofed up somewhere. नहीं, यहाँ पे r theta नहीं आएगा because it is not connected to the spring. This is connected to the rod. So when this moves r theta, the rod also moves r theta, the spring also moves r theta. But here, if you see, two things happen: the disc ka compression, the rod ka compression. So here we'll get only K1 r theta. Yeah. When will you get that also? If this rod had been connected here, then it would have made a difference. Have a look at this. So the main thing is the springs are getting compressed due to two things. One is a disc and one is a rod. And this is another one.
So why will there be tension in the rod?
Because the springs are pushing it.
Oh, right. Yeah.
The moment you displace it, the springs got compressed. The springs are pushing the rod away, na?
Hmm.
The springs are pushing the rod away. There will be tension in the rod. ऐसा सोचो ना, when you displace by theta, let's say if this point goes r theta, this rod will rotate theta, this will be theta, this will be theta, the lower part is being pushed up, isn't it? If you displace the upper part, the lower part has to move because it's a rigid rod. You cannot situation like this, isn't it? Rod तो ऐसा नहीं हो सकता है. So this thing actually displays like this. This is 3r theta. All got this? The most common mistake in this, they forget this part. The r theta. Either they forget this or they forget this. That K2 ka spring is actually getting compressed from both the sides. When you rotate by theta, the upper ka disc is pushing down and the niche ka rod is pushing up. The spring will get compressed by 4r theta. Whereas the upper spring will be r theta because the spring is not connected to the rod. It is connected to the disc. Clear? It's a good one. Let's see one more. This part is clear, right? This is one thing about a massless rods. You can take torque and you say torque is equal to I alpha and you say I is 0, not alpha is not 0. It works out. Let's see one more. We have a rod here connected by two strings, mass M and length L. Someone twisted the rod slightly out of the plane, meaning the rod is twisted by theta and released. Find time period. Length of the strings is L. ML is the mass of the rod and length of the rod. Strings are massless. What is the catch? Think. I'll give you a minute. You won't take the tension over. No, you have to take both the strings, right? It is tight. You didn't understand how the diagram is?
सर
It's
बट
like
जहाँ पे ऊपर
जैसा है ना, देखो ऐसा है ना, थोड़ा ट्विस्ट किया तो दोनों स्ट्रिंग्स ऐसा कर रहा है.
अच्छा ऐसे आई थॉट यू ट्विस्टेड इट ऊपर ओके
नहीं ऐसा नहीं. We
अच्छा
twisted it horizontally.
अच्छा हॉरिजॉन्टली देन
Okay, 5L by G. Let's see. This cough now, it comes and goes off every 3 days. I don't know what. I need to go to hospital. Let's see. What is the catch here? If you see this from the, the top view or the side view, this is what is happening. Let me show the diagram. So this is the initial position. You twisted the rod a bit like this. Let this be theta. Now, what you're interested is, but if you look at this thing here, the string, this is some beta. Let's call it some let's call it phi. You're getting the strings are twisted by a different angle phi. This angle is phi. So if you actually look at the tension of the strings, right, there are two components here. So this tension is acting like this. So there's a T cos phi and there's a T sin phi. So if you see the top view, the rod which you twisted it from the horizontal position, this is theta. This will be T sin phi. This will be T sin phi. Are you getting this? T cos phi will be up and T sin phi will be horizontal. Meaning इसका अगर components लिया ना, this will be T sin phi and this will be T cos phi. And you can clearly see there 2T cos phi will balance mg. Then I hope that diagram was clear. This would be T sin phi. This would be T cos phi. So here if you take torque about the center, this will be 2T sin phi into L by 2 is equal to minus I alpha. So 2T sin phi L by 2 is minus ML square by 12 alpha. For small angles, we can write that is phi. So T phi, and you can substitute that 2t ka value here. Mg by cos phi sin phi is L by 2 minus ML square by 12 alpha. LL goes off, 2 goes off. For small angles, tan phi is approximately phi. That would be mg phi is equal to minus L by 6 alpha. Alpha is equal to minus 6 MA आएगा 6g by L phi, and this is wrong. Why?
You need theta के terms में.
Yeah, basically alpha you're taking with theta, isn't it? We need alpha in terms of theta, not phi. Because when you displace theta, what you're getting is alpha. So what's the relation between phi and theta? Again, same thing. If you look at this thing, when you took this is theta, this angle will be how much? L by 2 theta. From the vertical perspective, this is phi and this is phi. So this is phi. So this rod says this length is L by 2 theta. The vertical string says this length is L phi. Therefore, both are actually equal. The horizontal displacement L by 2 theta should be equal to that L phi there. So from there we get phi is equal to L theta by 2 small l. Now take that and substitute here. You end up with minus 3g by L theta. That's your omega square. Clear? Got this? Next one. Got the thing, na, everyone? When you displace horizontally, it is L by 2 theta. When you displace vertically, it is L phi, and both should be equal because it is the same point. Clear, na, Anusha? Got this? Arjun, Aditya,
Yes, sir.
Neil, Rehan, Aryan. Perfect. Next thing. Infinite pendulum. What if we have a pretty long string? Now see, the catch is, till now, what we have solved, when you took a pendulum and when you displaced it by theta, this is what we did. We took the force mg, restoring force mg was like this and mg was like this. So we assume g is downward, that is, earth is flat for small lengths. But when you take really long pendulum, the problem comes. So if this was your planet, and let's say it's a long pendulum, meaning it is pretty close to the Earth, but the length is pretty long. The gravity is still constant only. Mass is close to surface, but just the pendulum is pretty long. Now, when you displace this by theta, this is the problem. The mg is toward the center of the Earth. The mg is toward the center of the Earth. Getting the catch? So mg ka direction is not in the same direction anymore. Mg got twisted. Even in the first case, it is the same thing. It's toward the center, but we ignore it because the length is too small. It really won't matter. So this creates some issues actually. Are you getting the difference between long pendulum? So this is a long pendulum. That is, length L is comparable to radius of the Earth. So here L is much smaller than capital. So what you have studied is that case 1 till now. What happens if you have a really long pendulum? Is the diagram clear? So let's see how will the restoring forces act on this guy. So this is length L. Let's say you displace again, the angle is quite small. Theta is still small. Let this angle be phi and this will be R. So this length here will be R phi. This length will be here L theta. So L theta is equal to R phi. That's your relation. So from here we get phi is equal to L theta by R. Now, M is here. This is the hinge. This is the center of the Earth. Now your restoring force mg is this way. So if you extend this line here, this angle is theta, this angle is phi. We know this angle is theta plus phi. So if you take the components here, this would be mg cos theta plus phi. And this perpendicular component will be mg sine theta plus phi. So restoring force is not mg sine theta. It is mg sine theta plus phi. Then the story is the same. Torque will be mg sine theta plus phi into L is equal to minus I alpha. For small angles, this guy will become theta plus phi. Phi is again L theta by R into L. I is minus ml square alpha. So we get alpha is equal to minus G 1 by L plus 1 by R into theta. That's your omega square. Therefore, the time period is 2 pi root over 1 by G into 1 by L plus 1 by R. Check out the proof. Clear? Then now see that formula, right? So this is the general formula for simple pendulums actually. 2 pi root over 1 by G 1 by L plus 1 by R. If that length is much less than R, it's your regular small pendulum. This is the formula for long pendulums. Huh? Then 1 by R will tend to 0. Then the time period will be 2 pi root over L by G, which we know. If suppose L tends to infinity, that means it's a pretty long pendulum, then 1 by L will tend to 0. Then the time period is 2 pi root over R by G. This is a direct question in mains. Huh? What's the time period for infinite pendulum? Most people think infinity because उनको लगता है यार 2 pi root over L by G, L is infinity. The problem is the formula itself has changed. The formula is not 2 pi root over L by G. This is a time period for infinite pendulum. If I give you L is equal to 2R, 3R, then put in the formula. This is a standard question. You can expect something in bits. Time period for infinite pendulum. Option में there will be an infinity. 2 pi root over R by G. Radius of Earth or radius of the planet. Check. Understood the difference? Right? This is the main catch. That mg restoring force is not vertical. It is toward the center of the Earth. That is why you're getting an extra angle phi. Whole thing gets messed up. So this is a more general formula to remember. Clear? So this is one concept there. So that's a theory and that's a question and concept, everything. So let's see one more. We have a pulley here. We have a spring. We have a block, mass M. This is a disc, mass M, R, and there's no slipping. Meaning, when you displace this, what will happen? The pulley also will start rotating. Meaning the pulley will rotate like this and the disc will come down here. In the previous question, what we did, remember, K equivalent, usme pulleys were smooth. Find time period for small oscillations. So here pulley rotates. See, I'll show you a normal way and then I'll show you a faster way. Disk, you know the moment of inertia, right? mr square by 2. First thing, when you displace this by theta, so if you displace this by theta, let's say alpha, this block will go by A. So on this, the tensions will be T1, T2, alpha. This is connected to the spring. So this is T1 and this will be K into R theta. On this side, the block will be T2 and acceleration. We are taking only the change in forces. All these are change in forces. Initially, tension is there. Initially, the spring is already elongated. We are not interested in all that. So here, if you take torque T2 minus T1, is equal to I alpha. And we know T1 is equal to KR theta. And we also know T2 is equal to minus MA. To solve this, you will get alpha is equal to some omega square minus theta ka form. That is one way to do, write the equations and solve. There is a much better way. Which I taught you in rotation, if you remember. Whenever you have a mass M attached like this, take the mass and attach to the point where they're connected to the pulley. Net torque method. So this diagram becomes like this. So now what are the forces here? So this is there. Now if you displace this with theta, this will stretch by R theta. So on the disk, the forces will be K into R theta. No other forces are changing. The torque will be K into R theta into R is equal to minus I net into alpha. K R square theta, I net will be disk is mr square by 2 plus the particle is mr square alpha. 2K by 3 mr. This is for the mass and this is for the disk. That's your time period. Make sense? If you have done this, you'll got the same thing. Isn't that how we do alternative? Replace the mass with the block at the point of intersection. Or you can say attach the block. This will be a net torque method. The string is connected to pulley. You can do it the regular way also. Equation 1, equation 2, equation 3. You just eliminate T1, T2 aa jayega. Clear? Take a break. Come back with 7 to continue from here. Any doubts so far? Any doubts so far? Chalo, I'll be back in 5-6 minutes. वो concept समझ में Let's see. So from next week onwards, you guys will be seniors. With juniors are, and next week the juniors are starting. And दोनों batches full हो गया almost. Next thing, see. Now, this is all what we did, right? Is all forces, torques, and everything. But there is another way to handle this kind of problems. Energy method. One, I don't like this because if I'll show you why. But there are some problems where energy method is the only way to solve. We will see that also. So for that reason, we need to learn. So this concept, right? What it says is, we know in an SHM the total energy is constant. So when you solve these problems, this is what we do. Let's say, example, we have a block of mass m. Step 1, displace it from the mean position. Let the velocity be v. So whenever you use energy method, this is what you do. Displace from mean by x, and let speed be v, and acceleration 1. Step 2, find the total energy. Step 3, differentiate. And compare with A is equal to minus omega square x. Now, in this problem, right, so the total energy will be the spring energy half kx square plus the kinetic energy half mv square. Is there any other energy? Now differentiate. Since the total energy is constant, the left side term will become 0. And this guy will become kx. The 2 will cancel. And this will be dx by dt. This will be mv and dv by dt. So dx by dt is velocity. Mv by dv by dt is acceleration. Vv cancels. We get a is equal to minus k by m into x. And therefore time period is 2 pi root over m by k. This looks fine. That is because this is a very simple case. But let me show a little more complex case and you'll understand the problem. Because in the net force method, right, the advantage we have is we always take the change in forces. That actually saved us, 1 or 2 steps. But here, this method, right, we have issues actually. We always have to find the initial positions and stuff. Let me show you one more example. But please have a look at the steps. Every problem that I taught you to this in this chapter, you can do with energy method. I just don't prefer it because I feel it has more steps than the force method which we are doing. Let me show you this example. Let's say we have a block hanging M. So remember, this is your natural length. This is your mean position. This distance is y, which is mg by k. Now displace by step 1. Displace the body by x. So this elongation becomes y plus x. Let the velocity be b. Now see the problem here. Now the total energy is spring energy half k x plus y whole square. Means you need to know that y. Kinetic energy half mv square minus mgx, because the potential energy also will decrease, isn't it? If you take the initial as a reference line. So this was your gravitational potential energy. This was your kinetic energy. This is your spring potential energy. There is a high chance you'll forget that mgx ka term. If you pull the block down by x, the displacement, there will be a potential energy. Now differentiate. Left side is 0. This guy will be k into x plus y, dx by dt. Y is constant, so I won't write that. Half mv square, 2 will cancel, mv dv by dt. And this is minus mg dx by dt. So this guy will be k x plus y into velocity plus mv acceleration minus mg velocity. And we know ky is equal to mg. So this term and this term cancels. This turns out to be a is equal to minus k by m into x. The same thing. If you remember this question, how we did with net force method, what did we do? The block was displaced by x. So the change in spring force is how much? Kx. Change in mg, 0. Therefore, kx is equal to minus ma. हो गया ना एक step में. Did you get the difference? The moment you take change in forces, I don't care what is y now. But here you need to take that y ka value, you need to take the potential energy ka value. It actually becomes slightly complex. So this is how you solve any problem with energy method. Let me give you one, you guys try. Clear? Understood the process? This problem now, let's try to do this energy method. Let's try this 45 with energy method. You already know the answer, so it'll be easy to verify. What is the step one? Displaced by यहाँ पे small x or theta. You will see how many terms will come. Like the force looks more intuitive. Energy works, nothing wrong with it. Because every time we take the change run, life becomes easy. Displaced by theta. So let this thing go by x, rotate by theta. So this guy will be 2 r theta. This will be r theta. This is x, so this is 2x. Let the velocity be v. What is the total energy? Half k1 2x whole square plus half k2 x square plus half m v square plus half I omega square. Lucky there is no gravitational potential energy. Differentiate. This thing k1, this would be 4k1 x dx by dt is v plus k2 x v plus mv acceleration plus I omega alpha. I is how much? Solid sphere 2 by 5 mr square. This would be minus 4k1 plus k2 into x plus ma plus 2 by 5 mr square. 1 r omega will cancel. 2 by 5 ma. We will be 5 by 7. 4k1 k2 by mx. Is that the answer? Yeah. Clear? Wait, there's a 2x whole square, right? 2 square बाहर आएगा. Clear with the energy method? The only place, where I saw some useful for this, if the springs have mass. So let me show you that question also. Let's say we have a spring here attached to a block here, the small m and k. The spring is having mass. Here the problem is when the spring stretches, the center mass keeps moving. We can't solve with force method. At least I couldn't figure out how to solve this with force method till now. And the mass of the block is much, much greater than small m. So in this question, right, so this ground is smooth. You can actually roam with this result also. So in these kind of questions, generally you will assume the velocity is linear. Meaning, when you took this spring here, this part of the string is going with v. This point is having 0 speed. That means different points on the string are going with different velocities. So since it is going linearly, we can write v dash is equal to, let's talk it as y. V by length into y. So at this point, y is equal to L, and at this point, y is equal to 0. So every point on the spring will have different speed. This information has to be given that the velocity will vary linearly on the spring. Now how to solve? Then I gave you this much information. Get this with the energy method. See, if I write the total energy here, half mv square, half kx square. So this is for the block. This is for the spring. And kinetic energy of the spring, because spring also has a mass. Now this is a problem that we don't know. But now we know the velocity profile. From there we can find at a distance x, we take a small piece dx. We can assume the uniform density because mass is much smaller. That's the reason we need that assumption. Then the kinetic energy of the spring will be half dm v dash square ka integral. dm will be total mass of the spring m by L dx, let's say dy. And what is the velocity? Vy by L. This will be half mv square by L cube integral y square dy. This will be mv square by 6. Therefore, the total energy is half capital mv square, half kx square plus 1 by 6 mv square. Differentiate. Zero. This will be mv acceleration, kx velocity, 1 by 3 mv acceleration. We get a is equal to minus kx by m plus m by 3. The time period is 2 pi root over. You can remember the result. That spring can be replaced by a mass of m by 3. Don't add, the masses are not same. Capital M and small m tau. Got this thing? So if the springs are having mass, this is the only method which will work. Force method doesn't work. Meaning doesn't work, at least I couldn't figure out. Because when you write F is equal to ma, the tension also will vary in the spring. So exactly which tension will you take? So it's confusing. So energy will be a savior in this case. So especially, right, whenever there are variable mass systems, energy is the best method. Think of like that. Variable mass or variable energy system. So if you see the spring will have different energy at different points. So this is about the energy method. You can solve all the Igla problems with it, but generally I would say just stick to your net torque method and the net force method, the change in forces method. If the springs are having mass, use the energy method. I'm sure you learned both the things in your classes. But I would prefer the change in forces one. Saves you 1 or 2 steps. Clear? Any doubts on this? Next thing. Torsional pendulum. Torsional pendulum, right? Torso means your hip. Ever did this thing on a swing when you're sitting? Instead of swinging, did you ever rotate yourself? And you rotate like this, isn't it? So just like, see, if you're sitting in the chair right now, right, sit straight and try to turn back without going back. You will see your entire torso will twist, isn't it? That's what we call as torso or torsional. So it's like a twisting ka thing. So when a wire or a cylinder is twisted, when you pinch your sister, right, that's a torsional torque. Pinching is torsional. See, now this I'm sure this example is much better. It generates a twisting. A more technical name is torsional torque. So questions are pretty straightforward on this. So if you have a disk like this, let's say this is O, this is A. If you twist this by theta, this is O, A becomes like this, meaning this thing got twisted by theta. And this torsional torque is proportional to theta. The torque is proportional to minus theta. This is your torsional torque, or this is your angle twisted. So we can write this torque is equal to minus k theta. Torque is equal to I alpha. Alpha is minus k by I into theta. So time period is 2 pi root over I by k. I is the moment of inertia about the axis and k is the torsional constant. So k, right, will tell you how difficult it is to twist a thing. More about this we'll talk in elasticity. Regarding this k, we will discuss in elasticity. So let me show an example. Questions are straightforward on this. For example, if you take a disk, they'll give you the k ka value. The time period is 2 pi root over I by k. I of the disk is root over mr square by 2. बस हो गया. If they give you a rod and if you keep it like this and if you twist it, same thing. Just put I is equal to ml square by 12. Now regarding that k ka value, the cylinders, of length L, radius R, fixed at the bottom. If you try to twist this cylinder, the torque comes out to be pi theta r power 4 by 2L into theta. This is the torque required to twist it. The k ka value is pi eta r power 4 by 2L, which is proportional to r power 4 by L. This eta is called rigidity modulus. We will talk about that in elasticity. For now, ignore that. And look at the function there. It is r power 4. Meaning, if you take two cylinders of same length, but let's say r, and let's say this is 3r. This guy is 81 times more difficult to twist. Again, one of the rare formula in physics with the power 4. So the thicker the cylinder, it becomes more difficult. It's proportional to r square, r power 4. And how we got this, that's a question for elasticity. So don't worry about that part. So exam mein dekhna ask a question like that. Someone is using a wire of length L and radius R, and another wire of length 2L and radius 2R. Then find the torsional constant. Then we have to use this. That's it. Torsional pendulum, there's nothing much there. You twist it by theta, you'll get torque, and this torsional constant ka thoda discussion that can go to advanced level. Have a look at this. Questions will be straightforward. They'll give you k ka value, and they'll give you need to find I ka value, put it there, and you're done. Any notes? Great. Next thing. The last part of SSM is damped oscillations. Now, mains mein is removed, but bits mein it is there. Not much. Advanced mein it is still there, so we have no idea. So what we will do, at least we'll finish off the basic part. Meaning basic one, I'm going to teach you everything. If it is not there, enemy will ignore.
Finish your previous page.
All right.
Previous page.
Previous page here.
Yes.
Done. So what is this damped oscillations? Let's take a simple case. Let's say we have a spring block system. Right? And let's say this thing is dipped inside a liquid. Let's say we have some kind of a platform. And this whole setup is placed in a liquid. This is liquid with viscosity. So there is some friction. So if air resistance or any dissipative force is present, again, we'll study for a special case. If F resistance is some minus BV, It can be BV square also. It can be BV 1.5. It can be anything. We study for linear variation. Meaning it's so complex. So here B is called damping constant. So what B tells you is higher the B, more the dissipation, more the resistance. V is the velocity. It's all theoretical, mathematical. You should know the results. So if you look at the body's URM, what are the forces acting on the body? Let's say if it is pushed down by X, let the velocity be V. The spring force will be Kx. Minus indicates opposite to velocity. So air resistance will be upward. Acceleration will be this way. So the forces will be Kx plus F resistance is equal to minus Ma. If you bring all to one side, you get Ma plus F plus Kx is equal to 0. If you write this equation, we end up with M d square x by dt square plus F, that is dx by dt, plus Kx is equal to 0. The minus sign is taken care in the direction, huh? So I'm just putting the magnitudes here. So what we have is a differential equation. Now how to solve this, they'll teach you in maths. You have a separate chapter for that. But we'll just take the solution for this. Now, listen to this thing. Like I said, ये सब तो आपको, you just need to, no need to remember all this stuff. Md square x by dt square plus b dx by dt plus kx is equal to 0. So for this differential equation, the general solution is given by x is equal to a into e power alpha t. How we got this? Don't worry about it. So from here, dx by dt will be a alpha e power alpha t. D square x by dt square is a alpha square e power alpha t. If you dump it in this, you end up with m a alpha square e power alpha t b a alpha e power alpha t plus k a e power alpha t is equal to 0. We get m alpha square plus b alpha plus k is equal to 0. The roots of this alpha is minus b plus or minus root over b square minus 4mk by m. So I can write alpha as minus b by 2m plus or minus root over b square by 4m minus k by m. So the final answer is what? X is equal to a into e power alpha t. So take this alpha, put it there. That's your answer. That's your x as a function of time t. So in this, how we got the general solution, that don't worry about it. Like I said, this proof is also not important. HSC may be important, nahi hai. Entrance also, mains also it's not there. But that's how we get a function like that. We need that thing, for me to explain you something. But please have a look at this.
Could you go to the previous slide?
Clear? Now, if you see these roots here, for this to exist, for this function, whatever we did to be true, Case 1, if b square by 4m square is greater than k by m, means the roots are real. What is the meaning of this? This is called overdamping. Meaning the function, right? This thing, if you try to put a graph, you'll understand it's called overdamping, means the system won't oscillate. There will be no oscillations. That is, when you stretch the system and leave it, it just aram se comes back to the initial position. And stretched and released, it comes back to mean and stops. Best example. Did you ever see when your classroom or office ka door na, when you pull the door and leave it, the door aram se closes. Meaning you won't see the door if you close it, the door won't fluctuate like this, right? The door won't flutter. So that spring actually to the door is a spring door is actually overdamped situation. The spring door, when opened and left or released, it comes back to initial position and stops. Tell me one thing, when you're going on your scooty, right, or bike or car, do you want the springs to be overdamped or underdamped? Just think about it. If the springs are underdamped, overdamped nahi hai, right, and you're going on the scooty and there's a speed breaker. After going over the speed breaker, what will happen? You will just keep oscillating, isn't it? You'll keep oscillating, you won't stop. But if it is overdamped, what will happen? The spring got compressed. When it comes back aram se. Isn't that a comfortable ride? So you can let that also as an example. So basically the shock absorbers in a vehicle are overdamped. You won't have that vibrations non-stop after this thing. If they're underdamped, you will be vibrating. The driver will vibrate inside. Shock absorbers in a vehicle are overdamped. This can be asked as theoretical questions. Find the condition for overdamping. If you take case 2, that is b square by 4m square is equal to k by m. The roots are real. This is called critically damped. There is no difference. Here also there is no oscillation. So tomorrow if you're teaching a robot how to do a surgery, right, you have to make sure all the systems are overdamped. Isn't it? Because if when you take a knife and if it moves like this, it should stop after that. You don't want the knife to vibrate. So overdamping systems, even though they lose energy, they have their own advantages. So the best difference to understand, right, overdamping and critically damped, if you put a graph, you will notice. If you plot a graph between x versus time, let's say this is starting from here, it's an exponentially decreasing function. This is overdamped. The difference with critically damped is this thing will come to mean position quite faster. That is a difference. In critical damping, it will reach the mean position in the fastest time. There will be no oscillation, but it takes the least time to come back to the natural state. That is an advantage. In critical damping, body reaches mean position in least time. That is the difference between overdamping and critical damping. In both the cases, there will be no oscillation. Have a look at this. So these first 2 cases, right, are just theoretical questions. The case 3 is actual where you have, one numerical, 1 or 2 formulas are there. Have a look at this. This is an exponential graph, right? It's a decay function. Case 3, if the roots are imaginary. This is underdamped. Again, we'll not go too much into this max part. You know, how to get a complex number ka roots and all. That you will learn in complex numbers. So for this differential equation, when it is underdamped, these are the roots. X is equal to a into e power minus bt by 2m into sine omega t plus phi. Omega dash t plus phi. This is not an exponential function. It's actually a sine function whose amplitude is an exponential. And this omega dash is given by root over k by m minus b square by 4m square. If you put b0, you'll get your regular formula. The time period is 2 pi by omega dash. So for this thing, the amplitude would be a into e power minus bt by 2m. It's if I try to put it on a graph, it starts here. It's a sine function, so it will be like a sine, but the amplitude is decreasing. You're getting how is it? The function keeps on decreasing. So it is oscillating, but the amplitude is decreasing. Sorry. There, these are the three formulas you need to remember. Let me show you what they can ask you. There are only two models they can ask you on this. These are theoretical questions, critical damping and over damping. Based on this under damping, there's only two what you call numericals. Have a look at this. You can put down the formula there.
We can go back. One more.
Previous one. Did everyone get over damping, under damping ka meaning? Not. Can you give me a case of under damping? Where did we see? Simple example, why if you keep a pendulum in a air resistance, the pendulum will slow down, slow down, slow down, slow down, eventually stop. So those are under damping cases. Over damping, the resistance is so high, you will just aram se come and stop. You won't oscillate on this. Let's say a question. The amplitude of damped oscillation is given by A is equal to A naught e power minus bt by 2m. Find the time when the amplitude becomes half and the energy becomes half. That's what generally they can ask you only these two things. They can play around with the B and all, but it's all based on that. Just substitute in the formulas and you'll get the answer. But these are two things they can ask. Mains mein to pura nikal hi diya, so whatever is there for advance only. Let's see. We will know about the portion mostly by next time before your mains exam. Bits mein to they won't go beyond this. HSC mein hai ye sab, but the integration differential equation is not there. They are only under damping case. Finish up last one for the day. With that, we're done with the chapter. Friday we'll catch up. We'll start off with viscosity, then we'll do surface tension and elasticity. Get it. The first one is easy. सिर्फ एक का place में A0 by 2 डालना था. लॉन आएगा ना. See for the first one. A naught by 2 is equal to A naught e power minus bt by 2m. Put ln on both sides. Ln of is e power minus bt by 2m. T will be minus
Correct.
ln of will be minus bt by 2m. So T will be 2m by b ln 2. What about energy? Remember, total energy is half m omega square a square. So energy is proportional to a square. So if energy becomes half, amplitude becomes a by root 2. Clear? Ln root 2, 2 power half comes out. They can play like this. They can ask you find the time when the energy becomes 1/3, energy becomes 1/9, so on. You just put in the formula and finish it off. So energy is proportional to a square and the amplitude is that thing. Clear with this? So that's the last one for the day. So there's a damped oscillation. So we have done almost 53 questions. So make sure to go through this and start solving. Don't delay it. Try to finish off, your classes ka booklet by at least next week. See, that's what I'm saying. When we start solving parallelly with me. Don't delay it. And I already know this chapter is over for you. So you should be able to finish it off. Aisa nahi hai, you don't know anything about it. Do make sure to go through this. We did some pretty good models also in the middle. Okay, with that, we'll wrap up for the day. So on Friday, when we catch up, we'll continue with the viscosity, the properties of matter will start. And the tests, right, were online. Do check it out. Even the last month, there are 2 tests, right? Mechanics and that. And this week, test was heat and thermodynamics and ray optics. All the 3 tests are online. So for people who are preparing for your upcoming major test, you can use them. That would help.
So
Okay.
after the module, what should we do for SHM?
Which one?
So after module, what should we do for SHM?
After module for SHM, you can try my booklet called level 5, level 6, or you can do Erudo.
Okay.
Or I'll post a sheet in the group today if you want.
No, sir, I'll do your module. Level 5.
Yeah. Anything is fine. See, that's what I'm saying. Don't get obsessed with the material. Getting it every material is good. आपका PACE का module जो है, they're taking it from Bansal.